My dear students, let me welcome you all to a new edition of physics. In this edition, we'll try to learn to understand the relation between EMF of a cell, terminal voltage, and internal voltage. By the way, terminal voltage is called external voltage, and internal is called lost voltage. What about the relation, if you want to know? Yes, let's get started. Relation between V battery, EMF of a cell, of course, V battery is the EMF of a cell, and external voltage. First of all, talking about Ohm's law applied to a closed circuit. In front of you, we've got a circuit that contains a battery, VB, and of internal resistance denoted by small r and external resistance R capital. EMF of a cell is defined as the work done in transferring unit charge, in transferring one coulomb throughout the whole circuit, through the external circuit as well as the internal circuit. Okay, so we can say V battery is equal to V external plus V internal. Okay, any voltage equals the product of current and resistance. So we can say VB is equal to IR capital plus IR small. The current intensity will be taken as a common factor. Okay, so V battery equals I between two brackets R capital plus R small. Okay, where R capital is the external resistance, R small is the internal resistance of the battery. This is Ohm's law applied to a closed circuit. Current through the battery is equal to V battery over R capital plus R small. It follows something we've got here, something which is very important. The current through the battery, okay, is determined from the formula V battery over R equivalent of the whole circuit. It means R equivalent of the whole circuit includes external resistances as well as the internal resistance of the battery. Okay, V external, as I said, is called terminal voltage. It has got another name. It is called terminal voltage. So external voltage is the same as the terminal voltage. And what about the internal voltage? Also has got another name. We call it lost voltage. So internal voltage is also called the lost voltage. Now talking about the relation between EMF of a cell and the potential difference across the terminals of the cell, across its terminals. Okay, to investigate this, we've got a circuit in front of you. We've got a battery. Across the battery there is a voltmeter, and we've got an ammeter, a rheostat, and a switch, okay, denoted by, yes, letter K. When the key is open and no current flows through the battery, okay, no current flows through the battery, the terminal voltage, okay, which is the reading on the voltmeter, equals V battery. So terminal voltage is a maximum and equal to V battery when no current flows through the battery. When the main switch is open, terminal voltage, reading on the voltmeter, is the terminal voltage. It's then a maximum and is equal to V battery. Okay. Why? Internal voltage at that moment is equal to 0. Why? Internal voltage is the product of the current and resistance. Current equals 0, so the product will be equal to 0. So V external terminal voltage will be equal to V battery when no current flows through the battery. V battery equals V external plus V internal. I'll explain this. Okay, so it is equal to V external plus IR small. So V battery equals V external. Okay, when I equals 0, as the product then of I and R equals 0. Okay, here we've got a circuit, and now we close it. Okay, the switch is closed. What about the reading on the voltmeter? Remember, reading on the voltmeter is the terminal voltage. When the key was open, it was maximum and equal to V battery. Okay, now we closed the key. Okay. When the key is closed, a current flows through the battery. So the reading on the voltmeter decreases because the value of the lost voltage is not equal to 0. IR small is not now equal to 0. Okay, so the reading on the voltmeter decreases. It was maximum. It was equal to V battery. But now decreases. It is just the terminal voltage. Okay. But if the current flowing through the circuit is decreased, the question is how? If the current is decreased by increasing the value of the rheostat, the terminal voltage, the reading on the voltmeter, increases one. Okay, increases because the internal voltage, which depends on the current, decreases. Okay. So V battery is equal to V external plus V internal. V battery equals V external plus IR small. V external equals V battery minus IR small. So when the current decreases, V external increases. We've got very important hint here in front of you. Your attention please. We've got a battery. Okay, no current flows through the battery. Zero current flows. What happens? Reading on the voltmeter is a maximum and it is equal to V battery. Let me say it again. When no current flows through the battery, terminal voltage is a maximum and equal to V battery. Voltage, okay, of the battery terminal voltage is equal to V battery. Okay, when no current flows through the battery. This is the first important hint. Okay, what about the second important hint? Your attention. Here we've got a battery which is short-circuited. We don't have any resistance. There is a maximum current that flows. Reading of the voltmeter, which is the terminal voltage, is then equal to 0. Voltage across the battery equals 0 when the battery is short-circuited. Okay, that is to say when the battery is connected to a wire of no resistance. A wire of no resistance, like what? A thick copper wire is connected between the two poles of the cell. No resistance, maximum current flows, then terminal voltage, external voltage is equal to 0. External voltage is the reading on the voltmeter connected across the battery. Now we've got, yes, questions. First question, what would happen to the readings on the two voltmeters? Voltmeter V1, which reads the terminal voltage. V2 reads the voltage just across R2. Okay, the question once again, what would happen to the readings on the two voltmeters if R1, value of R1 was increased? Okay, we'll take it one by one and we'll explain it. Okay, the answer is V1 increases, but V2 decreases. What about the explanation? Why V1 increases? Why terminal voltage increases, but voltage across R2 decreases? Okay. The explanation is as follows. Current through the battery is determined from Ohm's law of closed circuit. equals V battery over R equivalent of the whole circuit. Okay. So current through the battery is inversely proportional to the equivalent resistance of the circuit. Why? Because V battery, of course, is unchanged. For a given cell, for a given battery, V battery remains unchanged. So the current is inversely proportional to the resistance. Okay. Since V internal lost voltage equals IR small, so internal voltage is directly proportional to the current. R small is constant for a given cell. Okay. V battery equals V external plus V internal. So V external plus V internal equals V battery, which is constant. The relation between them is when V internal decreases, the external voltage, yes, increases. So we'll explain now. When R1 increases, the current through the circuit decreases. Okay. And so does the internal voltage. When the internal voltage decreases, the external voltage increases. So we managed to explain why V1 increases. R equivalent of the whole circuit was increased, current passing is decreased, V internal is decreased, so the external voltage increases. And what about the voltage across R2? It depends on the current, as V2 is equal to IR2. R2 is a constant, so V2 is proportionate to the current. What happened to the current? Yes, when R1 is increased, the current is decreased, so V2 is decreased. Okay. Another example for further explanation of the previous idea. We'll do it by using numbers, okay? In front of you, we've got a battery, 20-volt battery of internal resistance of 1 ohm. We've got R2, which is equal to 7, and the value of the rheostat was equal to 2 ohms, okay? We'll calculate the reading of V1 and the reading on V2, and we'll increase R1 and we'll see what would happen to the two readings. Remember, R1 is equal to 2 ohms now, okay? We'll do it, R equivalent of the whole circuit, 7 plus 2 plus 1, it is 2 ohms. Current through the battery, V battery over R equivalent, so it is 20 over 10, 2 amperes is flowing, okay. V external equals V battery minus IR small, so it is equal to 20 minus 2 times 1, 2 is the current, 1 is the internal resistance. V external is equal to 18. Remember this number, please. And V2 IR2, it is 2 times 7, 14. Your attention, we are going to increase the value of R1. Okay, it will be, instead of 2, we'll make it 12. Okay, and we'll see what difference does this make to the readings on V1 and V2. Once again, R equivalent of the whole circuit, 7 plus 12 plus 1, 20. R equivalent increases. Current through the battery, of course, will be decreased. Current equals V battery over R equivalent. It is 20 over 20. It is, yes, equal to 1. It was 2 in the previous example. Okay, it decreased to 1. Okay. And what about V external? It is equal to V battery minus IR. V battery 20 minus 1 times 1, it is 19. Okay, V external is increased. It was 18, but now it is 19. And what about V2? IR2, it is 1 times 7, it is 7 volt. In the previous, it was 14, so it decreased. Okay, we managed to explain it. And we'll take another question. What would happen to the readings on the 2 voltmeters? Your attention, the key is closed in front of you, okay? What would happen to the readings on the 2 voltmeters if R1, yes, was increased? Okay, V1 is the terminal voltage. V2 is the voltage across R2. and we are going to increase R1. Okay, V1 equals VB as IR is equal to 0. IR equals to 0, why? Because the internal resistance of the battery is given to be equal to 0. So V1 equals V battery, and it won't change because V battery is unchanged. Therefore, V1 remains unchanged. And what about V2? V2 equals IR2. Okay, so it is proportional to the current as R2 is constant. Okay, when R1 increases, the current decreases. Okay, and V2 of course decreases. It depends on the current. V2 equals IR2. R2 is constant, so it depends on the current. When increasing R1, the current decreases, so V2 decreases. And once again, what about V1? V1 is equal to V battery because R small is equal to 0. V battery does not change, V1 does not change. Another question, what would happen to the readings on the voltmeters if R1 was increased? Okay, your attention here. There is something interesting here. V1 and V2, okay, reads the same voltage. V1 reads the terminal voltage and V2 reads the terminal voltage. So both of them, okay, have the same reading. Okay. Once again, V1 equals V2. They are the terminal voltage across the external resistance. Okay, when R1, yes, increases, the current through the circuit decreases, the internal voltage decreases, so the external voltage increases. So V1 increases, and of course V2 increases because both of them are the same. Your attention, we've got something interesting here. V1, okay, equals V2 equals V battery, okay, if R is equal to 0. If R is equal to 0, V1, which is the terminal voltage, will be equal to V battery. V1 equals V2 will be equal to V battery, and of course they won't change by increasing or decreasing R1. If R is small is equal to 0. Since V battery is constant, so V1 and V2 remain unchanged when R1 is changed. Another question, what would happen to the readings on the voltmeter when R1, yes, was increased? Your attention, please. There is something tricky here. The reading on the voltmeter is not the terminal voltage. It is just the reading on R2. Your attention. Reading V1 is the reading on R2. Okay, so there is something tricky here. Okay. The reading on the voltmeter equals IR2. When the value of R1 is increased, the current decreases, so the reading on the voltmeter decreases as R2 is unchanged. What would happen to the readings on the voltmeter and that on the ammeter if the switch denoted by K2 is closed? It means we are decreasing the external resistance of the circuit. And we want to know the effect of this on the reading of the voltmeter. The question is, what is the reading of the voltmeter? Okay, reading of the voltmeter is the terminal voltage. Okay, so let me say it again. When the switch is closed, when K2 is closed, R1 is disconnected from the circuit, as if it was removed from the circuit. Okay, and what effect does this have on the reading on the terminal voltage, reading on the voltmeter, terminal voltage, and reading of the ammeter, current passing through the circuit? The key is closed. V decreases, but the reading of the ammeter increases. Okay. Another question, another different type of questions. When does the value of the terminal voltage of a cell equal the EMF of the cell? This is very important, and we explained this. When does the value of the terminal voltage of a cell equals the EMF of the cell? Okay, it happens in two cases. Terminal voltage will be equal to V battery in two cases. Okay, will you mention one of them, please? Okay, the terminal voltage of a cell equals EMF of the cell when no current passes through the cell. When no current passes through the cell. Also, terminal voltage of a cell equals EMF equals V battery when the internal resistance of the cell is neglected. When does the value of the terminal voltage of a cell equals, when does it equal 0? Let me say it again. When does the value of the terminal voltage of a cell equal 0? Okay, I can hear you saying it happens when, yes, the value of the terminal voltage of a cell equals 0 when the cell is short-circuited. What does it mean, short-circuited? It means the two poles of the cell is connected with a wire having no resistance. And what happens then? External resistance equals equals 0, so terminal voltage will be equal to 0. Let me say it again. When does the terminal voltage of a cell equal 0? When the cell is short-circuited. It means it is the two poles of the cell are connected to a wire which has no resistance. Okay, another question. When does the value of the terminal voltage of a cell become greater than EMF of the cell? This is a little bit more difficult. When does the value of the terminal voltage of a cell become greater than EMF of the cell? Okay, the value of the terminal voltage of a cell becomes greater than EMF of the cell while the cell is being charged. On charging a cell, the terminal voltage on the cell is greater than EMF of the cell. Okay, another question, choose. If the EMF of a cell of internal resistance, your attention, the cell has an internal resistance denoted by R small is equal to 1.5 volt. The terminal voltage of the cell when a current flows through it is, there is a current passing through it and it has an internal resistance. It asks for the terminal voltage is 1.5 is equal to V battery 1.5, more than 1.5, less than 1.5, no correct answer. A current of 0.2 ampere passes through a uniform wire, when a potential difference of 3.6 volt is applied across its ends. So we've got a uniform wire. What does it mean, uniform wire? It means it has got, uniform cross-sectional area. The area is constant, so resistance will be proportional to its length. When applying a potential difference of 3.6 volts, a current of 0.2 passes. So we've got enough data to calculate the resistance of the whole wire. A current of 0.2 ampere passes through a uniform wire when a potential difference of 3.6 volts is applied across its ends. Okay, the wire is shaped into a rectangle ABCD such that the length of AB is twice that of BC. Find the equivalent resistance of the wire. If an electric supply is connected, across A and B, points A and B. If an electric supply is connected across A and C. Okay. First of all, we need to calculate the resistance of the wire. Potential over current. It is 3.6 over 0.2. It is 18 ohm. Okay, the wire is uniform, so resistance is proportional to its length. So resistance of AB equals twice the resistance of the portion BC. Why? Because length of AB is twice that of BC, mentioned in the problem. So also RCB equals RDA. So we can say 2RAB plus 2RBC equals 18. And of course, resistance of portion AB plus resistance of portion BC equals 9. Okay, substituting for resistance AB, it is equal to 2 resistance BC plus BC equals 9. So we managed to obtain the resistance of the portion RBC. It is 9 over 3, of course. It is 3 ohms. And now resistance of AB equals 6 because it is twice the resistance of BC. Now we managed to obtain the resistance of each branch. Okay, what if the battery is connected across what? AB. When connecting the battery across AB, 3, 6 and 3 will form just one resistor of 12. And this 12 branch is connected in parallel to the 6 ohm branch. They are connected in parallel, product over the sum, 12 times 6 over 12 plus 6. Okay, it is 4 ohms. This was when connecting the battery across A and B. And what when we connect it across, AC? In this case, we've got 2 branches, one of 9 and the other branch will have a resistance of 9 ohms, and they are connected in parallel, so it's all easy. 9 over 2, it is 4.5 ohms. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.